Dear participants, we may start a new section named with Innovative Design of Climbing Walking Robots. The session chair is my colleague Armen Nunuparov. I invite you to chair this session.
Thank you, Artem, for the presentation. I'm a junior research scientist from the Institute of Problems and Mechanics, and today we will listen 4 reports in this session. For each report, I will have 10 minutes allocated for the presentations and 5 minutes for the discussion. I kindly ask all presenters to adhere to these rules. The first report has named Design and Development of a Multi-Robot System for Blockage Removal. The research was done in Russian Technological University Mira, and I kindly ask the speaker of this paper to start his presentation.
Hello, dear colleagues. Give me just a minute to demonstrate the screen.
Sure.
Okay, I hope the presentation is visible now. My name is Sekou Diane. I'm an assistant professor of Mira and one of the participants of this research. A design and development of a multi-robot system for blockage removal. First of all, it should be noted that multi-robot systems have a wide range of applications, including industry, defense sphere, farming, transportations, and also emergency and rescue sphere, where they can be used to remove, for example, blockages occurring after natural or industrial accidents, or maybe for rescuing people, and composition of a system from several robots allows it to perform the mission in a less time and with more efficiency. So the key problems of creating multi-robot systems are related to development of autonomous robots themselves, which are capable of performing some basic operations like grasping objects or like transporting them to the desired point. Also problem of motion control of these robots, a problem of network communication in a group of such robots, problems related to information processing, for example, environment model formation, so robots could understand which objects are located in which places. And the problems of the same importance are developing man-machine interface, knowledge formation, and self-learning for these robots, and planning behavior of groups of such robots. And additional problems are related to developing multi-robot system infrastructure, such as navigation systems and network communication systems, and so on. So in our research, we concentrate on the topics highlighted with a red line. Developing interface, forming knowledge on board of these robots, and planning their behavior. To take into account all these three problems, we stick to intellectual control system of multi-robot system, which includes blocks present on the slide. This is a knowledge database which stores information on how robots should react to one or another kind of situations in the environment. It includes learning system, it includes forecast system to prevent collisions between robots which move in dense environments. And in the core of the scheme lies the hierarchical control system, which has three levels: strategic level for mission planning, tactical level for task distribution, and execution level for agent functioning while they are moving along a trajectory or while they are trying to grasp an object. And user communicates with the systems via man-machine interface, and multi-robot system reacts to commands from user and reacts to state of an environment with information gathering system. So the main goal of our research was to implement this system in an experimental multi-robot system. It should be noted that robots depicted in the slide, they are by themselves complex objects which also are designed based on the hierarchical scheme. They also have these three levels, which are not related to mission planning or conflict prevention, but they are related to more precise tasks, which allow robot to be autonomous and to perform some actions which are decided on the level of multi-robot system without any external intervention. So by providing robot autonomy, we can rely on them while they are performing some missions, some scenario missions, which can represent multi-stage tasks. For example, such multi-stage tasks are building module constructions, be it it may be a wall of a building, or it may be a number of boxes in a warehouse, or the same approach can be used in numerous applications such as depicted on the left part of a slide. So to allow robots to perform the scenarios step by step, we should develop a model of the singular operation within this scenario. And the model of such an operation within a scenario may be designed on the basis of finite state machine theory. So the single operation within scenario can have 4 states. For example, it may not be available for execution at the moment. It may become available for execution. It may it may turn into a state of being executed at the moment, and finally it goes into a state finished. So while the system functions, the operations within scenario, they transition from state to state and allow the multi-robot system planner to take decisions on which operation to do in the next moment of time. On the other hand, not only operations within a scenario may be modeled as finite state machines, but also the robot may be modeled in the same manner. The states of robot include robot's initial readiness, robots performing the technological operations, and in some cases, robots failure. And both three cases should be also taken into account on the level of multi-robot system planning. And the final level of using this finite state machine model is a generalized model of technological process, where one state of the automator corresponds to awaiting for execution of a task within a scenario, and another state in this model corresponds to the process of executing it. There are some peculiarities in this scenario planning related, for example, to a situation when robot doesn't know the scenario beforehand. It knows only some parts of the scenario. For example, on the left part of the slide, the robot can't see object 9 and 10, so they don't figure in the dynamically formed scenario. Only those objects that are visible, they get into this scenario at the current moment of time. But while robot operates on these objects, new and new layers of them become visible, and they go into dynamically updated scenario. This was a part related to the planning of temporal order of operations within multi-robot systems.
I'm sorry to interrupt you, dear Sekou, Diane.
Yes.
We have only 3 minutes left before the next report.
Thank
so
you for your
I
notice.
can ask you.
I will get in time. So this is another part of the process. It's distribution of tasks. We use multi-parametric evaluation of agent suitability, which accounts for its distance to the goal objects and for amount of resources which allow a robot to go to that point. And the distribution goes based on the analysis of this matrix of suitability estimates. Here's a formalized view of this problem. And the experimental study that we decided to test while with research is depicted on the slide. Here are some robots allocated in initial positions. They should group into the starting point. Then, starting from there, some robots scout the area to find the blockage. And after the blockage is found and identified, other robots go to that place and remove the blockage. So this is a simple four-step process which is based on the described theory. Here are some details on the dynamic formation of the scenarios, because robot doesn't know how blockage looks at the initial time, so it should understand that while functioning. And here is the structure of the software that we developed. It includes all the strategical, tactical, and executive levels of control that were described earlier. For example, this is a part of software that relates to planning on the level of multi-robot system. Robots can both navigate the environment and transport some objects. This is a part of software related to autonomous robot. Autonomous robot can use technical vision to understand the geometry and the color of blockage paths. So after understanding this geometry, it clusters with blockage paths and dynamically builds a scenario which the robot must obey, which the robot must follow. Here is an illustration of our navigation system where we use cameras to correct robot odometer measurements. And here's a view of user interface where user can move robot both in manual mode and in automatic mode and in group mode of functioning. And finally, I would like to illustrate the process of our experimental setup, where robots no. Excuse me, it seems that some delays in the video. But this is the process. The first robot discovers the blockage. Does the video hang? I can launch it separately.
I'm sorry.
Excuse me.
I'm out of time. Yes.
Yeah, we're already 3 minutes late.
Okay.
So,
this is the illustration. The robots move, discover a blockage, and piece by piece transport the blockage paths to the target destination. So this is the final result that we obtained. Thank you for your attention.
Thank you very much, Diane, for your presentation. It was very interesting, and I think we all have a lot of questions for you, but I kindly ask everybody to ask them after this session in free time. Okay, and because we're a little bit out of time, but thank you very much. Next research called polyhedral rolling robot with expanded decade of icosahedral body, which is executed by a Department of Robotics in Kinda University at Japan. And I kindly ask the speaker of this work to present start the presentation. Thank you very much.
Okay, so I would like to share my slide. So,
dear Sergey, Diane, please stop screen share. Yeah, thank you.
Okay.